sac224n3. Okay, this is a cool problem. We got some completely unpolarized light coming in, hits a polarizer, which is polarized vertically. And the incoming light, we'll say, has an intensity I0. Gets through that polarizer where it's got an intensity I1. And eventually goes through a polarizer that's polarized horizontally. Comes out. It's actually got another one to go through, so there's going to be an I2. I'll call this I3. What I think is very interesting about it is, if these were the only two polarizers, I2 would be 0. This would make it so that I1 light is polarized completely vertically. The incoming, it's a mix, completely unpolarized light. And then the only thing that we get through this one is that does get through this is the vertically polarized light, and it has no horizontal component. So if this was the next thing it hit, you get no intensity. So you set that up, you get no intensity coming out, and then you could put another one in between, and check this out. Get one in there at an angle, polarized at some angle, given as, I'm going to draw a line at that angle, a longer one, given as 38 degrees with respect to the vertical. So I'll call that theta 1, and it's equal to 38.0 degrees. And of course, with respect to the horizontal, let's get a horizontal line in there as well. The polarization direction would be I call that theta 2, and it would be better to call it theta 2 and 3, but I'm calling them theta 1 and theta 2. Doesn't really matter. But that angle is going to be the 90 degrees, and I'll write it to 3 sig fig since that's what my other angle is written to. More importantly, out to one place past the decimal, since I'm doing subtraction. So that's 52.0 degrees. So 50 and 30 would be 80, and 210, so 90. So that's at 52 degrees, so that these two add up to 90. But what's wild, you pop that extra one in there, and this intensity goes from 0 to some non-zero value, which we're going to have to calculate. This would be in here, the intensity will be I2, and I think I said I was going to call that one I3, so I should have. That's I3 all the way through. So you pop another polarizer in between the first one and the last one. This intensity goes from 0 to some non-zero value, because you can break up this vertically polarized light into a component in that direction plus one perpendicular to it, so you get some light through that's polarized in this direction, and then when it hits this final polarizer, well, it's got a component in the horizontal direction, and so some of it gets through. We're supposed to calculate just what gets through. Let's say I1, you got completely unpolarized light hitting a polarizer. Half of it gets through, no matter what the direction of the polarization of the polarizer is. So I1 is equal to 1/2 of I0. Okay, now as far as I1, vertically polarized light hitting a polarizer that's oriented so that its direction of polarization makes an angle of 38 degrees with the vertical, means that I2, what gets through to this point, is going to be equal to I1 times the cosine of the angle between the polarization direction of the light and the polarization direction of the polarizer, which is 38 degrees. Oops, let's call it theta 1. I'm going to work things out with the symbols first and then plug them in later. Plug the values in later. And of course that's I1 itself is 1/2 I0, so I can write that as I2 is 1/2 I0 times the cosine of what I call theta 1 squared. Okay, let's take a look. I3 we got the light that gets through here is going to be polarized in this direction, 38 degrees with respect to the vertical, meaning it's polarized in a direction that makes an angle of 52 degrees with the horizontal, which is the direction of this polarization direction. So I3, what gets through this polarizer is the intensity of the light that's hitting it times the cosine of the angle in between the polarization direction of the light and the polarization direction of the polarizer. Horizontal polarizer in light that makes an angle of 52 degrees, whose polarization direction makes an angle of 52 degrees with respect to that, an angle that I call theta 2. And that's all going to be squared. So I2, however, we already determined to be 1/2 I0 times the cosine of theta 1 all squared. So replace that with that expression, and then we still got the cosine of theta 2 all squared. So now I just have to evaluate that expression, and I got the answer to the whole question. You can see it's not going to be 0. That's not 0, that's not 0, that's not 0. So I find it interesting that you do get some light through when you put a third polarizer in between the original two, which are making it so that no light gets through. This is going to be 1/2. I give the original intensity I0 as 16.0 watts per meter squared. So power per area. Let's make sure I got that right. 16 watts per meter squared was the original intensity. So I'm plugging into this expression. So 16.0 watts per meter squared. And then cosine of theta 1. Theta 1 is 38.0 degrees. And that does have to be squared. And then we got the cosine of theta 2. That's the 52 degrees. And that's also got to be squared. So you plug that bunch of numbers into your calculator. The easy part is the units. It's got to come out watts per meter squared. That's the only units that we've got. And it's going to, we multiply it. Half is unitless. Cosine of that is unitless. Cosine of that is unitless. So these are the only units in the whole expression. Turns out to be 1.88 watts per meter squared. Definitely non-zero. I mean, 2 out of the 16 watts per meter squared roughly are making it through, but still, it's more than 0.